Welcome everybody. So today I'm going to talk to you about equilibrium. It's our first video in a series of the equilibrium videos. And so what I want to talk to you about first is the definition of equilibrium. You might have heard this term in other sciences, but for chemistry, what it really means is that there is an equal, or that there are equal rates of forward and reverse reactions. So this is what they're talking about, that there's equal rates of forward and reverse reactions. So you might see this, and some of you in class have been like, why are you drawing two arrows? But you'll have your reactants, or whatever you're starting with, forming products. You'll have your products forming reactants. This reversible type reaction is showing how you can move from left to right, from reactants to products, but then back, products to reactants. Now, things don't start off in equilibrium. They require time. Sometimes it could be a minute or a few seconds. Sometimes it could be hours or days or even longer, depending on what the reaction is. But in order to reach this equilibrium state, you really need two main factors. One, you need a reversible reaction. So with a reversible reaction, you're getting the forward and you're getting the reverse. If we just had one of the directions, if we were just going from reactants to products, we wouldn't be able to establish these equal rates going back and forth. Instead, what we would have is a situation where we would just be forming products, the products would build up, and we would never go back to making reactants. That would be a case where the reaction would do what they call go to completion. So the reaction would go to completion. Now, the other thing is we need a closed system. And a closed system is very easy to do. We just close it off, put a lid on it, put a cap on it. If we don't have a closed system, sometimes what is produced will leave. Like if I had, a reaction going on here is a liquid and it was forming a gas, if the container wasn't closed, the gas would never go back into a liquid. Instead, what it would do is it would just float away outside of the container, and we would have a situation that would never reach equilibrium. Even if they were all liquids, the effect wouldn't be as drastic. But the problem is that the liquid, if it's volatile, could evaporate. And that could change the way that the reaction is occurring and stop it from reaching equilibrium. Or it could cause stresses to the system. And that's something that we'll discuss in detail later. The idea of stressing a system and then looking and seeing how the system reacts. It's a process called Le Chatelier's principle. Now, there are different types of equilibrium. There's a phase equilibrium, and a phase equilibrium, it could either be where you have, or is almost always where you have some kind of phase change. So we have a phase change. And something important about the phase equilibrium is, again, you need that closed container, you need that reversible reaction, but you also need very specific temperatures and pressure. So let's take, the most common phase change that we all talk about, something like H2O liquid becoming H2O gas, or H2O liquid becoming H2O solid. If we do H2O liquid to H2O gas, I need a pressure of 1 atmosphere, and I need a temperature of 100 degrees Celsius. If I have a different pressure, the temperature that this is going to happen at is going to be different. If I have a different pressure, the vapor pressure would be different, and that would cause the boiling to be different. So this phase change is boiling, liquid to gas at a specific temperature and pressure. I could have something where I have, freezing, H2O liquid and H2O solid. This is freezing and melting happening at the same time, 1 atmosphere of pressure, 0 degrees Celsius. Now let's say that I actually set up this experiment. I would look at H2O liquid and I would, put it at 0 degrees in a special freezer, and I'd have some H2O solid there, some ice cubes, and I would put it in there in a closed container. And I could leave it there forever. And what would be interesting is that if you were to come back in 10, 15, 30 years, 70 years, the freezer, contraption is still working, you would be able to see that it would look exactly the same. And this is because of our equal rates. We have rates going forward, rates going in reverse. Those rates are equal. There's no visible changes in equilibrium. And we'll talk about the misconceptions on the next slide, kind of give you an idea about this. The next type of equilibrium is solution equilibrium. And here we're going to mainly be dealing with aqueous solutions. So if we take something like NaCl and we dissolve it in water, we form NaCl aqueous. Now, we talked about this with solutions, how you are saturated. And that's exactly what you are. You have a saturated solution. And what we define this as equal rates. Equal rates of crystallizing, forming the solid, and dissolving. And again, I could make a closed container with some salt in it that's saturated. There'd be some solid on the bottom, some solid dissolved, and I could go away for, 100 years and come back and take that beaker out of its, compartment and look at it. And it should look pretty much exactly the same. The last type of equilibrium that we're going to spend a lot of time on is chemical equilibrium. And this is as I defined equal rates of forward and reverse reactions. So this would be where we have a chemical change. And, we could have something like our Haber process. That's what this is called. We'll talk more about that a little bit later. But I have my double arrow right here. This double arrow is illustrating that it's a reversible reaction in both directions, and that we have a chemical change going on. We have equal rates. And in all of these states of equilibrium, no matter what it is, whether it's a phase or a solution, which are physical changes, or a chemical equilibrium that has a chemical change, we're going to notice that when we reach equilibrium, this point where the rates are equal, there's no visible changes. And that's really important. And it's important to keep that in mind because people, have misconceptions about that. So the misconceptions that people have, the first one is that the reaction has stopped. And they think that it stopped because they don't see any changes occurring. But what's really happening is you have these equal rates. And so the reaction is dynamic. There are changes. It's just that the changes are equal in magnitude. The example that I like to think about is like, imagine if in your classroom, however many students there are, there's always 2 students that are leaving to go somewhere, the bathroom, the cafeteria, wherever. But as soon as those 2 students return, 2 other students will leave. So if you had 20 students in the class, you'd have 2 out, 18 in. Now, if you could look at that, if you're in the classroom, you could see those students and you would know that there's changes going on. You'd see the students leaving and coming, and you would be able to say this reaction's occurring. But imagine now if you were up in an airplane or like a hot air balloon, some distance that you could still see the students kind of, but you couldn't tell who they were. They're just sort of like, black specks or, little specks at that point. So what you would see is, you would see in the room that somehow or other there's something going on, but you wouldn't be able to tell who was who. And so all you would see is that there's a constant amount of students. There's 18 students in the room, and there's 2 that are not there. But you couldn't identify the students, so you couldn't tell that a reaction is actually happening. From your point of view, it looks as though it's just static. there's no change. That's what we get from here. We're looking in at these microscopic particles. We can't tell individual particles. So because of that, we can say, oh, particle 1,000,005 and 1,000,006 are leaving, and, particle 3 and 17 are coming back in. We can't tell that. We just get a general sense that there's no overall change. So that's one thing. And then the second thing that comes up a lot is that you have equal concentrations of products and reactants. This is also untrue, and it's untrue in the sense that all that you have are equal rates. Notice my example with the students with the 18 in and the 2 out. I didn't have 10 students in and 10 students out. That's a possibility, but in this case, it wasn't true. And a lot of times the Regents exam and other, exams that you'll take, that'll be one of the choices. You've reached equilibrium when the concentrations are equal. And it turns out that that's not the case. The concentrations are not always equal. It's possible, but it's not always equal. All that are equal are the rates. All right. One more thing before I stop. Instead of equal concentrations, use the term constant concentrations. By using constant concentrations, you're saying that they're not changing. You're not saying that they're equal. So we're going to actually do a lab on this, and we're going to do some, a nice lab where we do sort of modeling. It's no chemicals, but it's kind of cool to see equilibrium in action. And then we'll do some labs with chemicals too, and we'll get more in depth here and more detail. All right, thanks so much for watching.